This video is for Chapter 19 for honors and college prep. Chapter 19 has 3 large topics in it, so I'm going to split those topics up right here. It has kinetics, which is going to be your section 19.1 and 19.5. It has equilibrium, which is going to be your 19.2, and it has thermochemistry. Which is your 19.3 and 19.4. So this video is going to work on kinetics. So kinetics, or rates of reaction, I'll put the word kinetics, is a scientific word for rates of reaction. And that talks about the speed of a reaction. And before we talk about how to change the speed of a reaction, we're first going to look at a reaction in detail. So these are the things you need to be able to label on a reaction diagram. So we are going to draw 2 reaction diagrams. I'll start with this one and then we'll just leave room for that one. Reaction diagram will have energy on the y-axis and time on the x-axis. Sometimes I've seen it as reaction progress. Essentially, here is reactants to products. So we're going to start with reactants. And reactants will always turn into products. And the energy of the reactants and products will be different. And then in between one and the other will be some sort of mound. So mentally, I can extend the reactant and the product line to look something like that. You don't have to extend it because that's not officially a part of it. So the energy difference between products and reactants we will call delta H of reaction, or the energy of the reaction. If you are in honors, you learned 11.4 that says the energy of the products minus the energy of the reactants equals delta H. If you're in CP, you learned if you have reactants and you have to add energy to get up to products, then you will have a positive delta H. And you also learned if you have a positive delta H, then you have an endothermic reaction. Okay. The other thing we should label on here is the distance between the top of the hill and the reactants. So distance between the top of the hill and the reactants is the activation energy. And in order to make this reaction occur, you need to add this much energy to get it started. So this is the energy change of the reaction, and this is the energy needed to get this reaction started. It takes more energy to get this reaction started. Other things we should label on this one. At the top, we will call this the activated complex, the top of the mountain. And this is where you'll find intermediates. We haven't talked about intermediates. But if you're honors, you'll know what an intermediate is shortly. So that is reaction complex, or reaction diagram for an endothermic reaction. So obviously we have to do exothermic. So here's my energy. There's my time. This time, because it's exothermic, I need the energy of the reactants to be higher than the energy of the products. So I don't know. I'll put it over here. Reactants are going to turn into products. And there's going to be a mountain. I made my mountain smaller just so you realize the amount. It all changes all the time. So mentally, I'm going to extend the reactant and the product line. Same as over here. The energy difference between reactants and products is delta H. The energy difference between reactants and products is delta H. In this case, the products minus reactants is negative. Or the reactants lost energy to become products. So that's why energy was given off to the environment, and it's called exothermic. We also want to label the energy of activation. So once again, it's reactant energy up to energy of activation. Now on this one, it happens to be smaller, but you cannot say all exothermic reactions have smaller activation energies. It just happens to be smaller on this one. So let's say you have a reaction and you want to go faster. Well, then you're going to add a catalyst. And we're going to write catalyst speed up reactions by lowering the activation energy. Okay? So with red, I'm going to sketch the curve pretending now I have a catalyst in there. So it's going to look a little different. I'm going to have the same reactants and I'm going to have the same products, but this time the hump will be smaller. And now look, it takes this much energy to start this reaction. So this is a lot less energy than this. So this reaction is going to happen faster because it takes less energy. Over here, same game. Reactants, products are the same. I'm not changing the reaction. I'm just changing the pathway. So on this one, almost too small to label. So energy of activation goes there. So that's how we graph and kind of look at reactions. Next, we're going to look at ways to change the rate. So factors that affect reaction rate. And you've probably seen demos, or you will do a lab with this. Or to be honest, you have a lot of common sense here. So we'll do this kind of quickly. Factors that affect reaction rates. Concentration of reactants is directly proportional to rate. Which means if you increase the concentration of reactants, or you increase the amount of reactants you have, has to be reactants, you increase the speed of or rate of the reaction. One goes up, the other goes up. So they are directly related. Temperature is directly related to rate. So that means if you increase the temperature, you increase the speed. Or conversely, if you decrease the temperature, you decrease the speed. And I think in real life you've seen that. If you speed things up, this is why we use refrigerators. All food rots, but refrigerators keep it cold so that it rots slower. So that's a pretty good invention. Catalyst. Well, we just saw that it lowers the activation energy. So we know that that's how it's working. So catalysts increase the speed of a reaction. Particle size. So this is, if you have, I like sugar and I like coffee, so here we go. There's my attempt at a sugar cube. This sugar cube has a large particle size. And my spoon, you could laugh because I do not draw, has a small particle size. Which of these two will dissolve faster? This one. Therefore, they are inversely related. Can't spell, so that's all right. If you're my student, you know that already. Related to rate. So if you increase the particle size, you decrease the rate. That guy, only the substances or compounds on the outside of the cube can react. Over here, they can all react. So conversely, if you decrease the particle size, if you squish it up, you increase the rate. Now, if you're in CP, you are done watching this video, but if you're in honors, there's more fun. So here it comes. We're going to work some math now for honors. The progress of chemical reactions is the name of the section. Kinetics is the study of the speed of reactions. So rate is equal to the change in the concentration of the reactants over the change in time. Just like in chapter 18, brackets stand for molarity, which stands for moles per liter. So change in reactants over change in time is going to be kind of like rise over run, or change in y over change in x. That's all just algebra, so I'm just going to put in parentheses. It's good to have in your back pocket. So we'll work with rate laws, and what we'll do is say the rate or the speed of the reaction equals k, and times the concentration of the reactants raised to some unknown power. So let's go through this. What does the size of k mean? Well, k is the rate constant. A large K means a fast reaction. And then the order of reactions is really just the exponent, or the power. And we'll talk about that a little bit. If I want to write a rate law, how are they determined? Must be experimentally determined. Not determined with the balanced equation. So then let's look at some experiments. I think everything I just spoke about will make more sense once you actually see something. So, example 1. Let's go through one. Determine the order of the reaction for the decomposition of N2O5. And here's a reaction. And here's some data. It looks like they switched up the amount of the reactant, and then the rate changed as well. No surprise, as you increase the amount of reactants, the speed went up. Okay. So on this one, I'm going to pick 2 experiments. I'm assuming this was 1, 2, and 3, because the scientists would go in order, and figure out the order. So I'm going to write first a generic rate law. My generic rate law is rate equals K, concentration of reactants, raised to the unknown power. and it's asking for order, so it's actually asking for this guy right there. So I'm going to pick 2 experiments. It doesn't in this case matter. So experiment 1 divided by experiment 2, and I'm going to plug them into the rate law and divide them. So I'm essentially taking the data from 1 and dividing it by the data of 2. So watch how this works. The rate of 1 is 0.50. The k of 1 I do not know. I just miswrote, but I'm just going to keep going. The rate of 1 is this, 1.55 times 10 to the minus 4th equals k, and then the concentration of 1 is 0.50 raised to the unknown power. Give it a big long division bar. Now I'm going to do reaction 2. Those 2 numbers, where do those go in there? 3.10 times 10 to the minus 4th equals k, and 1.0 to the x. And now it's just an algebra problem, but I'll walk you through some of the algebra. I'm going to go left to right. 1.55 times 10 to the minus 4th divided by 3.10 times 10 to the minus 4th. Well, actually on your calculator come out to be 0.50 equals, the k will cancel with the k, and this right here is the same as 0.5 over 1, 0.1 rather, no, over 1 to the x. So 0.5 over 1 is 0.5 raised to the x power. So I just pulled the x back out, which you should know how to do from algebra. X is going to be an integer because you're not in college, so we're going to make it nice. So, could x be 0? No. Could x be 1? Yeah. There we go. And I would just run through 0, 1, 2, 3. If it's not one of those, you messed up the problem. Sorry. So the order of this reaction is first order reaction. And that's it. Let's try another practice one. Example 2. Let's determine the rate law for this guy. So on this one, I'm going to write my generic rate law again. So my generic rate law, rate equals K times the concentration of the reactants raised to the unknown powers. Now I need to pick some numbers, and I see here I have 2 reactants, so I'm going to have to do this problem 2 times. Last time I had 1 reactant, so I only did 1 of these. This time I'm going to have 2 reactants, so I'm going to do 2 of those. So let's pick 2 where something will cancel. So see how these 2 are the same? That would be a good match. So I'm going to do experiment 1 over experiment 2 again. I could have done 2 over 1. It doesn't matter. I'm going to do experiment 1 over 2. And when I do that, my A's will cancel, and I'll be left with B's and rates. So then I can solve it. You'll see how this works out. So the rate for number 1 is 5 times 10 to the minus 2 equals K times the concentration of A raised to the coefficient, or raised to the unknown power, and B raised to the unknown power. I'm going to do the same thing for number 2. 2.0 times 10 to the minus 1 is rate A, B, and that should work. Now comes algebra. So I'll switch my pen to my algebra color pen. You're not going to believe me, but put this in your calculator. It's going to equal, this will equal 0.25. These will cancel. Those will cancel. 1 divided by 2 is 0.5 to the y power. So is y 0? No. Is y 1? No. Is y 2? 0.5 squared. Oh my goodness, it is. There we go. So y is 2. So we just did one where A cancels. Now let's see if we can get one where B cancels. And I see experiment 2 and 3. So I'm going to take experiment 2, divide it by experiment 3, and do all this again. So here goes. And since I already determined y, why don't I go ahead and change that to 2? Just feels like I worked hard for that. I should use it. Experiment 3. And then algebra. Divided by that is 0.5. 0.2 divided by 0.4 is 0.5. X, not 0, is 1. So I'm getting there. So far I know that this is a 2, and I know that this is a 1. Since we're determining the entire rate law, let's go ahead and calculate K as well. Pick any reaction. 1, 2, 3. Good morning, Samantha. My children are waking up, so good morning, Samantha. I'll make breakfast in a couple minutes. So I'm going to pick an experiment. Samantha, should we do experiment 1, 2, or 3?
3.
We're going to do experiment 3. Thank you, Samantha. So we're going to plug this in for experiment 3, everything we know. So for experiment 3, I always write which one I'm using so my grader will be able to follow my work. So experiment 3, the rate, and now I'm going to watch my units. Molarity over seconds equals K, which I'm solving for. A is 0.40, and the brackets mean molarity, but I'm going to write it out now. And that's to the first power. And B, molarity, and that is to the second power. So I'm literally going to pull out a calculator and calculate in front of you, clear out all those problems. So 4 times 10 to the minus 1 divided by 0.4. I can't believe I did that on calculator in front of you, but there you go. Divided by 2 squared. So I'm just going to back that up because that's actually just 4. 2 squared. 0.25. So K equals 0.25, and I have some units. I have a molarity on the left, cancels with a molarity on the right. This is a molarity squared, which is going to go in the denominator. So I'm going to end up with molarity squared times seconds in the denominator. Okay? So this would be my K. So now the grand finale, my rate law is 0.25 times a to the first, b to the second. What does all of this mean? This means if I were to double the amount of A, the rate would double because it's first order, so 2, 2. If I were to half the amount of A, the rate would half. For B, if I was to double the amount of B, the rate would go up by 4 because 2 squared is 4. if I were to half the amount of B in my reaction, a half squared is 1/4 the rate. So that's what it means. This reaction is first order with respect to A, second order with respect to B, and third order overall, because 1 plus 2 is 3. So third order reaction, first order reactant, second order reactant. Now let's scooch on to our last piece in this chapter, reaction mechanisms. So what these are a chemist's best guess to how reactions occur. So I'm scooching back through my notes. Hold on. In this case, there's something up here, and the chemists are trying to decide what's made up there. Since this only has one hump, it has one intermediate. If it was to do something like this, then it would have 2 intermediates. And vice versa. Actually, I just labeled the intermediates wrong. Then it would have, it would have 2 parts. So we're showing you the basic ones. Elementary reactions are the reactions that they use to describe. So don't copy this yet. But these 3 are elementary reactions. They're baby step reactions. Intermediates are made in a reaction, then used up. And catalysts, I feel like, are the opposite of an intermediate. They are put in a reaction and used, then remade. I won't go through these. We're going to do one reaction mechanism. So giving the following proposed mechanism, so some scientists said this is how it happens. Write the balanced equation, list the intermediates and the catalyst. So here goes. First of all, kind of like Hess's law, we're going to add these 3 reactions. So I'm going to look through and see what can cancel. As I look through, I have a nitrogen on the left and a nitrogen on the right. See how that's an unstable form of nitrogen? That's why it's an intermediate, or that's why it's in this but not the overall reaction. This oxygen is on both sides of the arrows, so they're going to disappear, or cancel rather. And I think that should be it. Now I'm just going to pull stuff together. 2 hydrogens plus 2 nitrogen oxides yields 2 waters and 1 nitrogen gas. So this is the overall reaction. I'll put these things in the beaker and I expect those things to come out. I don't expect to ever see an N or O. Okay, so let's pretend. Oh, let's go ahead and label our intermediates. We said an intermediate is something that's made and then used up. So I made N and it got used up immediately. In another step, I made O and it got used up. Do you notice how N and O are never down here? Intermediates are not included in the reaction. Now catalyst, there's no catalyst in here. So I'm going to pretend that in order to make this reaction happen faster, you can add a happy face. And at the end of the reaction, you will get a happy face. Where do we list catalyst? So that's what a catalyst would do. There'd be a molecule here and a molecule at the end. Where do we list catalysts in the reaction? They're not reactants and they're not products. We put them over the arrow. And we knew this before. So intermediates and catalysts are not in the overall reaction. Let's write the rate based on this. The slow step determines the speed of the reaction. So in this case, the scientist says the rate of this reaction, and we don't know K, depends on H2 and NO. In mechanisms, only mechanisms, I'm going to use the coefficients as the orders of reaction, which I can only do in a mechanism. So it's first order with respect to hydrogen, first order with respect to nitrogen monoxide, and second order overall. Look, those orders do not match the coefficients in the balanced equation. That's why we don't use them. We can only use them if it's the slow step of the mechanism. And that should be the end of kinetics.